Welcome to today's BiD Lab seminar. I'm Armando Fox, and I have the pleasure of introducing today's speaker, Zach Pardos. Before we get on with the actual talk, as always, thank you very much to Yahoo for sponsoring the delicious food that we're eating that you in TV land can't see or smell. Zach Pardos just joined UC Berkeley as an assistant professor. He's got a joint appointment in the School of Education and in the School of Information. And I was pretty excited when I went to his interview talk because he's really working at what I think is a very interesting intersection of educational learning sciences and data mining, and especially with all the activity around MOOCs and so forth, which, as you can see by my shirt, I am a supporter of. I think there's really interesting work that could be done, and some of the stuff that Zach is going to be talking about today, I think is representative of the kind of things that I'd like to see more of us doing at Berkeley and elsewhere. So, thanks very much for listening in TV land. Without further ado, Professor Zach Pardos.
So I'm Zach, and I just started settling into this position in October. Settling into a mild but popular flu also. So you want to keep your physical distance, but not intellectual distance. So I'm going to be talking about a model of proficiency that comes from the intelligent tutor land that's been permuted a bit to fit MOOC. So this talks about performance prediction with the goal of down the road scalable remediation. And I came to the conclusion that the title that went out had one too many colons, and it's like picking the first title and put it under the second. That pretty much fixed everything. So you might be interested in this talk if you're interested in proficiency models. You might be interested if you're looking for an introduction to a model of learning that's based in cognitive science. And this is also an opportunity for me to introduce myself to you by way of a taste of a piece of project that I'm involved in. Okay, so this most of this talk was presented in Memphis, Tennessee. Thus, Elvis. Not me when I was younger.
Thank you for putting that.
There is a similarity.
Yes, I play guitar too. Educational Data Mining Conference is where this was presented. It's in the sixth meeting. I'm the program co-chair of the 2014 conference. If you have any questions about papers you think of submitting there, feel free to bounce them off. So, why do research in MOOCs? Well, we all are interested, that's why we're here. But there's a buzzword of adaptation that's been around a lot. That's a little bit overused, but I make the case that with MOOCs it's worth reviving. For one reason is that MOOCs are prescribed in a far different way than intelligent tutoring systems are prescribed. And that is, where does the buy-in happen? Where is the subscription? What level is it at? And with intelligent tutoring systems such as Cognitive Tutor or Assessments, it tends to be at a district level where a school system will buy into computer technology and assign it to students to use. So the students themselves aren't opting into it. And so with intelligent tutoring systems, you tend to have students who are in the same grade, studying the same topic. So very low variance in terms of the population. Whereas MOOCs, they're self-selecting. And you just run the gamut of backgrounds in background knowledge, but also learning objectives of the students using MOOC. So there's a lot of variance out there, which is right to be captured by models and data mining. So I don't need to tell you what edX is, but the course that this talk is studying is 6002X, Circuits and Electronics, which is the inaugural edX course that was run when this was called MITx. And so here's the anatomy of the course. Here is the enrollments. There's 154,000 enrolled. 108 entered the class, and then...
What's the difference?
So 154 clicked enroll. 108,000 when the class began showed up on the home page, showed up and entered the course. So a lot of them just enrolled and didn't even bother. And then 7,000 successfully completed the course, which is your typical funnel of participation. So the components of the course, you had lecture videos, 434 of them, 37 homework problems, 105 lecture problems, about 1,009 book pages, 12 labs, 145 tutorial videos, which were different than the lecture videos because they concentrated on examples of homework for the most part. 2 exams, midterm and final, wiki page, and then a discussion board. And so here's the interface. You have the accordion view of the videos interspersed with lecture checks that ask you questions about what you just saw. And so here are the lecture video example. Homework problems. So the homework problem name is here. Homework 1, problem 1, energy, and then it has these 2 subparts. So it has a blurb here and then 2 questions that refer to the blurb. And then lecture problems look very similar. They have blurbs and answer fields, but they're worth less. And in fact, they're not worth anything in the grade. And then book pages, each page is tracked as a separate URL. Labs, videos, and wiki. So here's a breakdown of the course problem types and then how many subparts you have in each. So on average, the lecture problems had 2.7 subparts each. Homeworks had 5.3. You see for midterm and final. And then you see how much that was worth in terms of grade. Part of the relevance of going over the total number of subparts is if you think of breaking this space down into factors and what kind of skills are related to these questions, you're probably not going to want to break it down into more fine-grained than 289. Otherwise, you're going to have more skills than you have questions. And that's an important distinction in terms of the granularity that students have to answer questions. So for instance, in the cognitive tutor, you'll have questions that are broken up into subparts that are very, very granular. So you might have 15 subparts to a single question. And so in the cognitive tutor, they break algebra into 3,000 skills. In this case, 3,000 skills applied to 289 subparts won't get you very good
But wait a
identifiability.
minute. I could readily see that some of the subparts in different problems need exactly the same skills. So no collection like that and mapping back to the same kind of skill. Let's say one subpart is doing an addition.
Yep.
Well, addition may come up in 50 different problems, but it's always the same skill.
Absolutely, you could have multiple.
So why do you have this explosion of the number of skills that you extract from all this?
Where do you see that explode?
Well, you just mentioned it before.
The 3,000 skills?
Yeah.
So the 3,000 skills is in a separate tutoring system. So I'm contrasting what you might call a skill model, which is how many skills you're using to describe the pedagogy and the assessments. The granularity of that skill model for a system like this, or for this course with these number of subparts, may not be the same size of skill model that's appropriate for a different context.
I see. So what would be the number of skills that you would extract or associate with this course?
It's an open question. It's an empirical question. It's a question for the course instructor. But for example, in the cognitive tutors, there's thousands and thousands of steps, which are the granularity of answer fields. So
Okay, maybe.
So
it's
there's an
just a
order of
working
magnitude.
issue. So I can see various subproblems, various steps.
Yeah.
If you list them individually, that's one thing. But skills for me is a different thing. So maybe I confused what you call skills as kind of the number of steps, individual steps that appear somehow in the whole course here.
Yes, it's a different mapping. So in the cognitive tutor, the steps tend to map onto a very specific cognitive skill. It's very granular. Whereas here, it's different parts of the homework model. So they were not created with that kind of cognitive task analysis in mind. They weren't created from a cognitive model. They were created from a cognitive, which is an abstract. Right, that was a little bit of a slide. So for this analysis, we did not use the whole data set, but used a subset. And that subset was 10 randomly selected lecture problems, 10 randomly selected homeworks, and then 5 midterms and 5 finals. and then 2,000 users were sampled out of the 7,000 certificate owners. Part of this was because we didn't scale up our analysis models quick enough. They are scaled now, so any reasonable order of data size. So I want to give you a feel for the type of data that was being worked with, and it's a very transaction event log based data set. So I'm going to walk you through what Sarah did in this course after she first saw this homework. Actually, this is a lecture check. Okay,
Can you
so
read the small thing? I cannot read what
sure.
you
So it's this the circuit diagram shown that has a source voltage and a resistance. That says the strength of the source is 10 volts and the resistance of the resistor is 50 ohms. What is the power dissipated in the resistor in watts? And what is the power entering the source in watts? Okay. So what we have in the data is Sarah went to this resource, which is the lecture tech problem, spent 1 minute and 52 seconds there before answering incorrect to the first part. She answered 500, really naive attempt because it was just 10 times 50. This was her first attempt at answering. Okay. So she goes back to a video which she remembers might have been relevant. Video 1 from lecture sequence 1, video 8. And she spends 58 seconds on this video, maybe rewinding or pausing, and she sees V over R over here, voltage over resistance, and she thinks she's got it. She goes back to the problem, says, okay, it's 10 over 50, 0.2, and then opposite magnitude, entering the source, negative 0.2, clicks check, and she was incorrect on both. It was the second attempt on the first question, first part, and first attempt on the second part. So now she goes to the recommended book page. She's slowing herself down now, saying, okay, maybe I need to think through this and learn something. She goes to book page 27, spends 38 seconds there. First page in circuit fractions. She sees I equals VR, and she remembers P equals IB. And so now she goes back and applies that. But now she's more deliberate. She does one subpart at a time instead of both. 10 times 10 over 50 is 2, and then she gets checked, it's right on the third attempt, and then answers the second subpart correct on the second. Okay, so how do we model knowledge in this scenario? That's the question. And the answer is, for this, we're using a model of knowledge called knowledge tracing, or a derivative of that. This is an example I often show students when I was teaching in, assistant teaching in middle school, which is to ask them, what explains this response pattern? You have a student answering incorrect, and then correct, and then incorrect, and then correct, and I ask them to predict that blue circle. And they say they'll probably get it correct. And I ask them why, because the percent correct here is 50. So why would you assume that the student's going to answer correct? And they say, oh, well, because they've learned it. And I say, so what I see what you are not seeing is knowledge. Knowledge is increasing, therefore you assume that the student's going to answer correct at the end. And a very naive level, that's what knowledge tracing is. And knowledge tracing is represented by a probabilistic model. Classic graphical models and Bayesian models to get fast inference. It's also very nice for hypothesizing causal relationships between different elements, and very good at capturing temporal effects. It also has the opportunity to be interpreted. So, a little blurb about knowledge tracing, introduced in 1995 by Corbin Anderson. It's John Anderson of the ACDAR theory of skill acquisition. Computations based on a variation of Bayesian calculations proposed in 1972 by Atkins. And there's been a number of different extensions, a number being on the order of 15. So a couple things that knowledge tracing is. One is the hidden Markov model, and the second thing it is a pairing of the hidden Markov model with a model of knowledge. And that is an association of steps or questions in the system with skills. And skills, questions can be associated with multiple skills. And skills, of course, can also be associated with multiple items, so that longitudinally you can Parameters can be learned with EM, maximum likelihood fitting, or a number of different other fitting procedures. This is used in practice in cognitive tutors, the Andes physics tutor, assessment system, among other systems. So it's a very simple model computationally. There's these 4 parameters and no other. There's prior knowledge, the probability that a student knew the skill before starting. The learn rate's the probability that if they didn't know the skill, they will know it at the next opportunity to answer a question of the same skill. There's a guessing rate, which explains the probability that a student will answer correct if they do not know it, and then the probability of a student answering incorrect if they do know it. And you need guess and slip because you almost never see what you might call a perfect learning sequence, where it's a string of contiguous zeros followed by ones. So you need this to account for the noise. And there's other interpretations of guess and slip. So
I have a question on that.
Yeah.
I mean, the various red bullets you have, they were all different questions, right? So that means there's always a little additional knowledge needed in order to get to the next progression.
This.
Right? It's not the same question all the time.
Well, so actually for this, it's, I didn't say this, but for some skill K. So this is assuming that all these red
Okay, so
circles.
there's more abstract level. If there were different questions, but they're testing the same skill, if you can properly capture what that skill is,
Right.
right, of course.
Which is a big piece.
Right,
of
because I mean, is subtraction or addition the same skill or not, right? For instance, I'm making this up, but if you put it as the same skill and it really isn't, then at some point, you know, the blue dot is still negative because it's the first subtraction that shows up.
Absolutely. And there are, there's a whole area of research which is that factor exploration. One's called learning factors analysis, where it takes an existing model of knowledge. It says, let's say addition and subtraction are the same. We're going to call that one skill. And what it does is it splits. It experiments with splitting skills.
Based on evidence like that.
Based on evidence like this and seeing which
Makes sense.
hypothesis.
So you could discover what you really
Yes.
the individual chunks of skills are by having a lot of data.
Empirically. Right. So I'm going to go, for time purposes, I'm going to go a little quick through this, but for viewers at home, or when you have viewers at home, you can go over this. But this is the latent, it's a binary, so you know it or you don't know it. And then there's observe, which is also a binary, which is did you get this question correct or not. And forgetting is assumed to be 0 most of the time. In the canonical form of this model, it's assumed to be 0 because in the context where this model typically exists, students are answering a given skill typically in one day. So you won't see it over multiple days. So it's reasonable to assume they're not forgetting within one session. But that assumption can be relaxed. So this is the part I'm going to go over quickly. I apologize, but this is explaining how knowledge tracing works. This is how it generates data. It's a Bayesian network, so it can be generated. And based on these parameters of the world, this is how it might probabilistically generate both the student knowledge sequence and the student response sequence. Now, typically, you're not going to want to generate student response sequences unless you're doing simulation studies, which I might get to at the end. Typically, what you want to do is observe the responses and infer the latent. So here you'll have a response of incorrect. You want to infer the probability that they knew it at that opportunity. And to do that,
So can you clarify your term? You graph showed the same things on the transitions and is that because you're repeating the same problem or they really shorthand for different values for each different question?
where is
Well, is the question here, is it the same question or is it a different question?
it's a different question of the exact same skill.
Alright. So but all right, is the assumption that when you put these weights are the same for the transition probability?
The transition probabilities between every question is the same
But just within the skill.
within a skill, right? So there's a P of T, which is the learn for every skill. Now, it's reasonable to relax that assumption and say the probability of transitioning to knowledge, to knowing a skill, is contingent on what you just saw, right? Even if it's a a question of the same skill, it might differ in its pedagogical value in some way, where you might want to hypothesize that each question has a different learning value, a different learning transition. So this is that idea is the seed for going towards automated remediation, where we might be able to infer the learning value of resources by relaxing this assumption that they're all the same.
Just to clarify, is the learning, like what's causing the learning in this case? Is it the application of the prior problem? Is it seeing the solution to that problem? Is it going to be some learning materials in between the two problems?
So in the case of this course, for certain, a source of learning is the feedback, the red X or the check mark. Right? Getting feedback that you got a question right or wrong has a learning opportunity associated with it. If you're not taking into account anything else that they do between answering here and answering there, what this P of T is capturing is them going to a book page, them going to a lecture video. The average amount of pedagogy that is sought between opportunities is captured in that P of T.
It seems like you're throwing away a lot of information since you actually have traces involved.
Yeah, I agree. So wait for 5 slides and I deliver on information. Or start. So what I'm describing here is the canonical form of knowledge tracing, where you have these 4 parameters per skill and you don't vary it anymore. So as I mentioned at the beginning of this talk, MOOCs have a lot more variance in it than your typical system where this is applied, so you might want to vary it and allow for some sort of personalization. So here the probability of knowledge is assumed to be 0.037 given prior of 0.4, and then given you observe incorrect response, and then after a correct response and making the P of T calculation, the probability of what they know is 0.6694. The systems usually use the magical 0.95 to declare. These are just applications of data. So in the KBD calc, which was about predicting student responses in the future, all that's done is you make those same calculations I showed based on the sequence that you observed, and then you use the P of T transition to predict the probability of knowledge in the future, which monotonically increases if you don't have the probability of forgetting there, and then you use the likelihood that use the guess and slip parameter to predict correctness on the question.
Zach,
Yeah.
does this model capture any notion of uncertainty when you're extrapolating into the future?
In what sense? Where?
So, for example, say the last 2 latent states of the knowledge is what we're trying to predict, right? So we're extrapolating, and you have 79%, 83% said. But the uncertainty, I would think, would as you extrapolate out 10 questions,
Sure.
you would say, well, probably 100% with plus or minus 100%, something like that.
I mean, this particular model doesn't have any kind of confidence intervals involved, this one, when it doesn't see any more responses, it assumes you're going to take the typical curve that P of T did.
So where do the red or orange numbers P of T, K come from?
So the orange ones up to here come from the calculations I just showed. And then going from 75 to 79 is taking 75 plus 1 minus 75 times P of T. So you're adding to this the probability that they learned it. Apply the learning transition formula, which is the probability they know here, plus 1 minus that probability, so the probability they don't know it, times the learn rate. And that's how you get the next
Okay,
prior.
the learn rate is just fixed.
Yeah. And so the probability of guess can vary, these parameters can very severely impact the inferred probability of knowledge for students. So if your system is dictating how many correct in a row, let's say, problems a student needs to answer before they no longer need to answer questions of that skill, the probability of guess can really affect that. So here we have these parameters, a prior 0.5, a probability of learn of 0.2, and a guess of 0.14 here. And with this, a student will reach that 0.95 magic mastery level after the fourth opportunity given this sequence of responses. So incorrect on the first one, and then correct all after that. Whereas if the guess parameter, everything else is the same, but the guess is now 0.64, it takes until the 8th opportunity. So that's twice as much time that the student needs to spend. There are some issues of local optima that you need to pay attention to. So restart VM and restart often to avoid some of these. I have to just wave my hands there. So back to this. How do we model knowledge in this scenario? And applying the model that I just mentioned, it looks a little bit like this, where each K is an opportunity to answer, so it's only these lines of answer. And then you see here part 1 incorrect. On the second click of the check button, parts 1 and 2 is incorrect, etc. So this is a retrofitting of that model to this status set, or at least to the response part of the status set. So each line here is a different student and their sequence of responses. And so the game here in terms of performance prediction is to train the parameters based on a training set or cross-validation. And then a holdout set, you'll predict each stepwise response. So for instance, the algorithm will say, okay, you have your holdout fold and cross-validation. You have a student who's answered the first step. Do you care to make a prediction about that step? And the algorithm will say, well, it's got to be based on prior knowledge because we have no other evidence of the student. 0.24 probability correct, et cetera, et cetera. We'll go through each one, asking, and then we have the actual response and predicted, and use your favorite error metric for goodness sake. So there were a couple of challenges faced here. Ways in which that canonical model needed to be changed in order to adapt to the MOOC. And one way is there was no skill mapping. So a nice thing you get with intelligent tutoring systems is they've spent hundreds of hours creating a cognitive model. So that matrix that maps skills to questions has been very meticulously created. But in MOOC land, we have hundreds of MOOCs now across various different subject areas. And in post-secondary education, mapping it at that level doesn't make sense. So what do we do to get that skill mapping? The other issue is multiple responses in one transaction, which is easy to address. You just have multiple observed nodes per time slice. And then multiple attempts allowed in the system. The issue with this is that in terms of guess and slip, which response count might you think the most information exists in? Is it the student's first response to a homework question? Probably not, because they know they get all the attempts in the world to answer it correct. So the first response might be a heuristic attempt. It might not be a true reflection of them thinking and reflecting what they know. At the same time, their last response is almost always correct because it's answering until correct. So how to deal with that? And then what you were alluding to before, you have all this other information, why not incorporate it? There's nonlinear pathways to the system, so modeling influences from the resources that are interspersed with the assessments is another step. And this one is more future work. The others have been done. So for the skill mapping, we used a very naive way of creating that what's called the Q matrix, which is the association of questions with skills, and that is to assume that every homework problem is its own skill, is teaching its own concept, and that all the sub-questions of the homework problem are belonging to that same skill. It's a really poor mapping, but it's what would suffice for this study. So completely superficial mapping of the skills. The multiple responses I mentioned just have multiple observables. And then for modeling multiple attempts, what I decided to do is represent the variance of information that's in each attempt by varying the guess and slip parameters based on the attempt. So the guess and slip can be thought of as modulating the amount of information about the latent that you get from an observed response. So if you have a guess of 0 and you see a correct response, you know 100% that the student knows the skills because there's no probability that they answered correct without knowing. There's no guess probability. So the higher the guess probability, the less information you can infer about the latent from a correct response, and the higher the slip probability, the less amount of information you can infer from the correct response. So by conditioning the guess and slips based on the attempt count, you can basically construct an information curve. Yes, Mark?
Doesn't this leave out a third option between yes and no, which is wrong? So they could have gotten it right, but for the wrong underlying knowledge? Misconception?
That's guess, isn't it?
No, it's different than guess.
But it's incorporated.
Well, it's a different thing, right? Because guess is yes versus misconception, which really I think is a fundamentally different thing, which is harder to undo in some ways than a guess.
So there's probably, I would guess that a misconception that you have that leads to a correct answer is a bit of an edge case. But I would say that most of those edge cases should be caught by a proper knowledge model.
Or to take a more realistic case, maybe misconception leads to a wrong, which is different than a guess also. A wrong answer caused by a misconception as opposed to a guess.
So there's sort of two schools of thought which are convergent, but of representing knowledge. One is representing as a binary construct. You either know this or you don't, and anything that leads to you answering it incorrect is for the most part due to you not knowing it. There's another school of thought that my colleague Mark Wilson has been a part of constructing, which is a learning progression idea, where you start with all the misconceptions in the world and you slowly knock them off. Right?
So I thought for a lot of our physics instruction, that was the whole point, is there's a lot of misconceptions and they have to unlearn them in
Right.
physics instruction.
So they are separate approaches. I would say that a misconception just factors into not knowing it here. It's not specifically isolated.
But, I think you need to look across questions a lot, across topics before that distinction becomes clear. But we did see pretty strong correlations between errors in the minor score. So yeah, there are apparent misconceptions that is the predictors of different questions, specific different wrong answers to different questions.
So along those same lines, there's something that hasn't been done. Is you could look at the most common wrong answers, which might be indicative of ones generated by misconception, and provide a different guess and slip for those most common wrong answers. I'm thinking, well, what's the remediation that you provide to that how model might help? I suppose if you observe someone answering in a common wrong answer way, and then you observe students somehow reaching mastery after having been caught up on those misconception snags, you can look at the traces of resources that they went to and maybe recommend those resources to the people who.
Yeah, I know the way to finish, but a little, this model is sort of based on the blank slate model, which is, been sort of debunked a lot. But the students start as a blank slate, and they just need to have knowledge put into them, and so they're either guessing or they don't know. And I think that's obviously a good simplifying assumption to begin with, but I think it'll make a lot of errors because there is this reality that a lot of errors are caused by partial understanding of misconceptions. Not to say it's not a good way to start, but it does seem like that Anderson school is this sort of blank slate building.
Well, no.
I was just going to say, this model, like just looking at the model, it definitely can't model correlations between incorrect answers because you have some probability of guessing on each problem that's independent of guessing on the other problem. And
So that's not quite correct. So the canonical version of the model has the same guess and slip for every question that's involved in a certain skill. But you can change that and have a different guess and slip for every
but
question.
even if you have different guess probabilities for every question, you can't model correlations. Like if I get this problem incorrect, then 9% chance of getting this problem correct.
So basically arrows between questions.
Yeah. I mean, only within a topic, it's all correlated through the network, but I guess there's no abstraction across topics.
And sort of a complementary issue. On that power comment that we had before, suppose the student actually understands the concepts, knows you have to calculate the current, multiply it, and all that, but then by doing the calculation ahead or on the calculator screws up and that gets decimal point wrong and the answer's plain wrong. So if you see that in writing in an ordinary test as you do today, you know, to say, okay, they got everything right, just the final multiplication step is wrong and give them credit. Do you have the possibility of maybe at some point suspecting that they understand the physics concept, but that's just the way you're handling the calculator? And would you then go back and actually give them just plain thing, multiply those two numbers, and see how many times they get it wrong, and realize, no, you better practice your multiplying here, because otherwise it's perfectly right.
Right. So identifying what they're weak at is a credit blame assignment problem. It's an inference assignment problem. So if you have multiple skills associated with, say, calculator use with a problem, given their previous responses and knowing what was associated with those previous questions, you can infer, oh, well, the calculator was the weak thing. What you do for remediation after that is a little bit different. So I would, I think, Marty, your criticism is correct, but I would deconflate two aspects. So one is the probabilistic graphical model approach, and the other is the cognitive model end. And so this approach is much more utilizing graphical models than it is utilizing a Andersonian breakdown of cognitive tasks. So in looking at MOOCs, like I said, the weakest point of this work was basically pulling a cognitive model out of the air, right? So in many ways, completely flaunted the Andersonian approach. But I would say for this, when it comes to MOOCs and the different background knowledges that apply and the different concepts that exist, a lot of work needs to be put into creating that Q matrix, creating that knowledge model, right? How do you represent knowledge? Maybe it's misconceptions, maybe it's more conceptual. If you look at the Andersonian models, it's really hard to find where the concept lives. It's all these really granular skills. So it's really about mapping out knowledge, where it's gained, what it is, what students are seeking. These are all very big questions. But I think they can be brought to bear with graphical model approaches, perhaps not with strictly Andersonian skill models.
You got to start somewhere too. You start simple and then build up.
Right.
But I do think, as a teacher, certainly the misperception problem is harder to overcome than the missing knowledge problem. And I think that a lot of the data that maybe doesn't get explained might be better explained by this sort of need to undo that might not be captured in the current design.
Absolutely. And sort of in the spirit of some of these educational data mining competitions, I think it's really important to compare models with the same evaluation set and see how the different models talk up to one another. But jumping off that idea of starting simple and then getting more complicated, you could model knowledge as not a binary. You could say it's a multi-state, and that those states could include you have a misconception, right? So,
I mean, I think the higher order bit of this, in the interest of letting you get to more stuff, is anytime you take a model and you apply it to a domain, there's some assumptions the model makes in order to be tractable, right? I think if you just, in terms of clarity of exposition, just saying what the assumptions are, and just being upfront about the fact that this is a starting set of assumptions, and depending on what type of course material you're applying this to, you may need to relax some of those assumptions to do useful work. Right? But I think this probably addresses a useful subclass of stuff. As always, part of the challenge is spelling out what the assumptions are that sort of circumscribe the subclass, like no correlation carries over from one question to another, can't distinguish between guessing versus wrong answer because of misconception. Right? I think it doesn't make any of this invalid. It just probably makes it easier to frame, should I use this in my course, right? Because as an instructor, my operational desire is to know, if this gives you an interesting result, is it appropriate for me to use it with my kind of material or not? And understanding what those assumptions are might help you create material for which it's more likely that your model would produce something that I can interpret.
Sure.
Does that make sense?
Yeah. Yeah, I am interested in that. Does does having multiple taggings of items that should be correlated together, does correlating them through a tagging of a skill solve that?
I think if you have the multi-state knowledge,
The multi-mapping.
and you have negative.
All right, so the sort of future work is the question of, well, what's being captured with the PFT? We have all this fine-grained information about where they went. Why are we just assuming that everything needs to be stuck into a PFT? That captures the amount of learning from one period to the next. So the approach to that is, well, why don't we model where they've been and also associate a different PFT depending on where they've been. So this is that same model, but instead we now have the knowledge which is PFT conditioned on the resource they were just at, and you can have resource types of learning from answering. So if you just answered something here, you're learning from feedback, so that can be resource type 1. If you went to another homework problem and then came back here, that can be resource type 2. If you went to a video, wiki, discussion, tutorial, book, etc. And so these are just resource types, and you can associate, try to do this inference of which resources are leading to the highest PFTs based on these assessments interspersed with resource access. But you can also get more granular. Instead of saying there's just a resource type, there's also a resource URL. So this isn't just a book page resource. This is book page 79, and attributing different PFTs to 79. In a multi-value knowledge representation where there's many different states, a different book page could be better for transitioning you from one state than it is for transitioning you from another state. That almost. So the last thing is a simulation study where I asked the question of, well, how much data do you need to make these kinds of inferences accurately, given this number of parameters, these number of hidden states, et cetera, et cetera. The answer, without going into detail, because I don't think I have time, is about 7,000 for the number of resources that are in the scope of a homework problem in this course, which is exciting because that's around the order of students we have at the end. And the more students you get, the more data you have, the more accurate you can be with these inferences. So that's an exciting part of MOOCs where the more data you get, the better the analytics can get. So the prediction was done with a 10-fold cross-validation, actually 5-fold cross-validation, trying to use different models on the same cuts of data. So the basic model, which was just the retrofit model, and then the count model that conditioned the probability of guess based on the attempt count, and then another model which lets each subpart have a different guess slip, which is then deviating from that canonical model, and then the item count, which is combines the two. So this is AUC, so higher is better, and this is over the 2,000 student data set. And the solid lines are the different types of assessments that are predicted. So you have all the homeworks, all the lectures, and the exams. And then here's the different models: the basic, the count model, the item, and item count. So with more complexity in the model, we do get better prediction accuracy, but there's not a significant difference between item and item count, while there is a significance between basic and count. So the biggest jump you see is between count and item, which means capturing the variance among questions that are associated with the same skill being this very lazy description of all the homework problems in a given homework are the same skill. So acknowledging that there are actually differences in performance between the two, which is the biggest bump. It's also worth noting homework was the easiest to predict, and lecture checks were the hardest, and exams somewhere in between. And then you see the dotted line is, instead of using the full 2,000 data set to do the cross-validation, only use 200. And while we do get a significantly inferior fit and prediction, the order does remain the same. So if you did find yourself in a situation where your model, for one reason or not, was complicated enough, we hadn't done enough optimization where the 2000 was bordering on intractable, scaling down to 200 users still give us the same level. So another way to think about this is how hard would it be to predict mastery in any of these areas with this skill model that comes out of the superficial structure of the course. So future questions are, what would this fit look like compared to a different skill model? So what if you assumed every question was its own skill, that they were connected? What if you had a subject matter expert come and cluster questions, maybe longitudinally, so a skill that appears in one homework will also appear in another one? In the current form, we can't do any of that because we're only looking at a skill appearing in one homework. And this is just RMSE, which is the same orderings. So one of the conclusions is that it worked all right. AUC of 0.65, nothing to have a party about, but we did capture some variance there. Attempt count had an interesting result where there was actually more information in an attempt the longer a student in the higher attempt counts. So the more you attempted a question, the more indicative your response was of how you might respond to different questions of the same skill. So, using alternative knowledge representations as future direction. There's several different approaches in the EDM literature to do this. Finding a signal in student resource viewing history. So one might think that if you knew where they've been versus if you don't know where they've been in terms of resource, you should be able to do better at predicting their future performance. But in order to do that, there's a number of different questions which all relate to figuring out where students are learning and how they're learning here and asking the right questions. And I think if you do ask the right questions with the right breadth, you can find that signal.
So I guess the key question now is, how good is good enough? Because, I mean, predicting 100% what the students will learn and how and all of that, I mean, why is that going for some academic paper? But if it's good enough to essentially take the right action and then steer the student to the right kind of advice or kind of resource, that's good enough. And so the question is, how good do you have to be in your prediction in order to give them most of the time the right remedies?
So I think the only way to get at that answer is to run an experiment where resources are recommended to the student based on this model and see if it improves one of two outcomes, whether it reduces attrition and whether it improves the speed of learning or just how many people graduate the course, how many people pass the course, or what their average scores were, right? Does this improve outcomes in the course, right?
Of course, whether you have attrition or not and whether they will finish, it probably depends even more strongly just on the tone, how you give them the feedback. So you tell me you didn't know that those resource 17, right? Just drop out immediately. The person, almost right, and here I have a secret little remedy for you, and they stay in. So they've been completely swamped by the tone of feedback.
Which is why this is also a very important HCI model.
Yeah.
It's a model called MAN. It's about the end of the
Following relegation to everything that you can go out of these models, but why not talk about relegation sounds to me like once you detect the problem, then you try to fix it. But intervention, you actually get to prevent it.
I guess I think of intervention as going both ways, but typically responding to a diagnosis of an improper state of the student and doing intervention. But being more proactive, so one way to be more proactive instead of when a student gets something wrong, recommend something to them, is if you can diagnose their state early on and just recommend a sequence, a different sequence to the course, right? Not necessarily when they get things wrong, but something that's based on their background knowledge and something that's based on their learning objectives. Just really morphing the course to that student and what they know and where they're going.
So following up on that, I think for that you might need a little bit better prediction, but ideally you would have a course where they almost never fail, because you have enough data accumulated in their rate of learning. You know just how much more you can tell them. They have a very high chance of getting it right. It comes success after success, rather than take steps that you gave and they fail and then you have to do remediation.
That's right. So one of the tensions there is where do the models stop and the pedagogy creation, where does that begin, right? So when you're running a residential course, you have to worry about the next lesson making too big of leaps, right? So do you fill things in? You still have a finite amount of time. So so maybe there's 5% gain that these models can contribute. Maybe it's 15%. But I don't suggest that it's all the picture, right? But there's definitely some data-driven assistance that can be used to improve courses.
So it's after 1 o'clock. Thanks, Zach. I don't know if you're planning to hang out and answer more questions or.
Sure.
Great.
If there's